Hey everyone, and welcome. So, we're going to dive into something I find absolutely fascinating today. How do you teach a computer to understand time? Not like a clock, but the way time flows in a story. The way we do? It's this incredible puzzle that sits right at the intersection of language and code, and the solution? Well, it's just so clever.
All right, let's just jump right in with a little puzzle. Think about this. How does a computer actually get the difference between I ran and I was running? One's done, finished. The other, it was happening, right? For you and me, that's instinct. It's totally intuitive. But for a machine, that's a huge, huge logical problem. And that's exactly the kind of thing we're going to crack open today.
So here's the fundamental challenge, right? It's all about translating our human sense of time, which is, fluid and continuous, into something structured, something a computer can actually compute. It's like we see time as this flowing river, but a computer needs to see it as a series of distinct snapshots, frame by frame.
And this really gets to the heart of it. The old school way of thinking about this in linguistics was what they called dense time. Think of it like a perfectly smooth number line. Between any two moments, no matter how close, you can always find another one. It's infinite. And for a computer, that's a nightmare. It's just too messy. Computers are much, much happier with discrete time, a clean sequence of separate moments. Just like those frames in a film strip we were talking about.
So the big question is, how do you bridge that gap? How do you get from the messy river to the clean snapshots? Well, the solution is this really brilliant idea that comes straight out of computer science. It's called situations as strings.
And really, at its core, the idea is wonderfully simple. It basically says, hey, what if we represent any event, any situation, not as a continuous thing, but as an ordered list, a string, just like in programming, of individual facts or observations? It's kind of like telling a story by just stating one key thing at a time.
Yeah, exactly like this. A simple story gets broken down into a string of different states. So you have state 1, the sun is shining. That's a fact. Then an arrow to the next fact, a door opens. And then the next one, a person enters. See? It's a clean, logical progression. It's something a computer can follow step by step, no problem.
Okay, so that's the basic idea. But let's dig in a little deeper and see how this model is actually built. Because it's not just about listing things in order. There are a few key ingredients here that give this whole thing some serious power.
This model really stands on three main pillars. First, you've got your observations. Those are just the basic facts, the building blocks of our string. Then, and this is super important, you have inertia. It's a bit of a fancy word, but it just means we assume things stay the same unless something actively changes them. And last, we have granularity, which is what gives the model its awesome flexibility.
Let's zoom in on that inertia idea because it's really cool. Let's imagine a really simple starting point. We've got a room, the light is on, and the window is closed. Okay? Those are our two starting facts, our two observations.
Okay, now something happens, an action. Somebody opens the window. So what's our new state? Well, the window is now open. But notice the light is still on. Why? Because nothing happened to the light. It just persisted. It had inertia. And this is so crucial because it means the computer doesn't have to restate every single fact about the world every single time something changes. It's super efficient.
And this isn't just a random idea, by the way. This concept of inertia is borrowed straight from classic AI research on how to model actions and their consequences. It makes the whole system way more logical and efficient. And honestly, it's pretty much how we think about the world, right? Things just kind of stay as they are, unless something happens to them.
All right, on to that third pillar, granularity. And this is all about how much detail you want to see. You can zoom in and out. So at a really low detail, zoomed out level, we can describe a whole event with just one single observation, like this. She made breakfast. But, and this is the beautiful part, the model lets us zoom way in. That same exact event, she made breakfast, can be broken down into a much more detailed string. First, she took out a pan. Then, she cracked some eggs. Then, she cooked the eggs. We can see all the little steps. And this power to adjust the level of detail, to change the granularity depending on what you need, that's what makes this model so incredibly useful.
Okay, so we've got our observations, our inertia, and our granularity. Those are the building blocks. But so what? Why does any of this matter? What's the big payoff here? Well, when you put all of these pieces together, you get a framework for analyzing language that is just remarkably powerful.
I mean, the advantages are huge. First off, it gives us a real concrete way to solve that whole ran versus was running puzzle we started with. But it goes way beyond that. It lets a computer make these really subtle distinctions between different kinds of situations. It's flexible, it's powerful, and maybe the coolest part is that it builds the solid bridge between the worlds of linguistics and computer science. And just to give you a quick taste of how deep this goes, the model can even tell the difference between two kinds of situations. One is just described, based on what is stated to be true. The other is characterized, based on what you can logically figure out from the evidence, and that's a huge deal. It's the difference between an AI that just spits back facts and one that can actually make logical inferences.
So here's the bottom line. The really crucial point is that by thinking about time and events as these neat, orderly strings, we're giving computers a tool that smashes through the limitations of those older, messier models. It's a practical, manageable way to get a handle on the super slippery concept of time in our language.
When you step back, you realize that looking at language through this kind of computational lens, it isn't just a gimmick. It's a genuinely powerful and flexible new way to analyze one of the most basic things we do as humans, how we talk about and understand time.
And that kind of leaves us with one last really big thought. If we can get this right, if we can truly teach computers the grammar of time itself, just imagine what kind of new stories they'll be able to tell. What new things will they be able to understand? The possibilities there, they're pretty mind-blowing.